WASP 76b. In astronomy, sometimes the best way to begin a journey is to exaggerate, to go straight to the extreme. WASP 76b is that, a planet that pushes conditions to a point that, a few decades ago, we would have considered impossible. It lies a few hundred light years away, in the constellation of Pisces. It orbits a star similar to the Sun, but at a ridiculous distance, about 12 times closer to its star than Mercury is to the Sun. That means a year lasting barely 1.8 Earth days. In less than 2 days, it completes a full orbit. So close to its star, the planet became tidally locked. It always shows the same face to its star, like the Moon to Earth. It has one hemisphere condemned to eternal day and another trapped in perpetual night. There are no sunrises or sunsets for a hypothetical observer on its surface, only one incandescent side and another immersed in a permanent twilight. WASP-76b is an ultra-hot Jupiter, a gas giant, its size inflated by heat, larger than Jupiter, though with a similar mass. The radiation it receives puffs it up, makes it less dense, almost as if the star were trying to tear away its atmosphere in violent tugs. On the day side, temperatures hover around 2,400 degrees Celsius. It is hotter than many red dwarf stars. At those temperatures, complex molecules do not survive. They break apart. Metals vaporize. Iron, which on Earth we associate with bridges, beams and tools, there becomes a gas and forms part of the atmosphere, like water vapor over an ocean. The famous description of this planet speaks of iron rain. The idea is simple, though extreme. On the day side, iron exists as vapor. Winds and the planet's rotation push that superheated atmosphere toward the terminator, the zone that separates day from night. As it crosses into the night side, the temperature drops by more than 1,000 degrees, enough for the iron to condense, form clouds of tiny metallic droplets, and eventually fall as molten rain, not a gentle drizzle. Models suggest winds of up to 18,000 kilometers per hour between one hemisphere and the other, more than 10 times the speed of a commercial jet. The entire atmosphere functions like a supersonic conveyor belt, carrying metal-rich gas from one side to the other, cooling it, condensing it, and letting it fall. Poetic exaggeration? The physics behind it is quite sober. We know that iron is present in WASP-76b's atmosphere because we have seen it indirectly using high-precision spectrographs mounted on telescopes, such as the Very Large Telescope in Chile. When the planet passes in front of its star, part of the starlight passes through its atmosphere. Each chemical element leaves a signature, a set of lines in the spectrum. Those iron lines appear shifted, broadened, unevenly distributed. Not only that, they vary depending on which part of the planet is in front at any given moment during the transit. In the data, something striking appears. Iron does not seem to be distributed uniformly. There are differences between the planet's morning limb and its evening limb. The most logical interpretation is that some of the iron condenses and disappears from the gas phase on the night side. That leaves a subtle but measurable imprint on the way it absorbs light. This does not mean we have a camera recording metallic droplets falling onto a sea of gas. What we have are light curves and complicated spectra. From them, atmospheric circulation models reconstruct the possible climate. Some recent studies even discuss to what extent the iron rain is as abundant as initially thought. What matters here is not the spectacle of the image, but what it reveals. We are beginning to distinguish chemical differences between one side and the other of a planet we do not directly see. In recent years, WASP-76b has become a laboratory for exoclimatology, a place where techniques are tested to map temperatures, winds and composition in 3 dimensions. Not only iron has been detected, but also other heavy metals and possible exotic oxides. Temperature variations have also been measured between the most strongly illuminated point and the regions already approaching night. With these data, numerical models are adjusted, corrected and compared again with new observations. And just when it seemed we had already labeled this planet as simply a metallic hell, something even more peculiar arrived: the possible detection of a glory. On Earth, a glory is an optical phenomenon resembling a circular arc of light, sometimes seen from airplanes when the sun, the observer and the clouds are aligned with great precision. It is produced by the diffraction and interference of light in nearly spherical droplets. It is delicate, difficult to observe, and depends on an almost perfect geometry. On WASP-76b, space telescopes such as Cheops and TESS have observed a strange asymmetry in the brightness of one of the terminators. During several transits, that region seemed to reflect more light than expected. The proposed explanation is that it could be an exoplanetary glory. If confirmed, it would be the first time this phenomenon has been detected outside the solar system. For a glory to exist, the planet's clouds must be composed of very uniform, spherical and stable droplets. That implies a surprisingly organized atmospheric structure amid the chaos of extreme winds and temperatures. It tells us that even in a world where iron may be reigning, delicate configurations of light and matter can form. The combination of metallic rain, supersonic winds, and a possible glory makes WASP-76b more than a curiosity. It is proof of how far we have pushed our observational capabilities. From Earth, with instruments distributed or across several continents and satellites in orbit, we are able to infer not only which elements are present in the atmosphere, but how they move, how they condense, and how they reflect the light of their star. This planet also reminds us of something else. The categories we use, such as hot Jupiter, are convenient labels. In reality, each world is a particular case. The conditions on WASP-76b have no equivalent in our system. There is no Jupiter with iron rain we can study up close. That is why this type of exoplanet is so valuable. They force us to rethink ideas about atmospheric circulation, high temperature chemistry, and the limits of matter in extreme environments. If, in a world like this, metal transforms into vapor, cloud and rain, it is worth asking what might happen when the dominant element is not iron but carbon. The next planet in our journey takes that question to the limit. For years, many astronomers imagined it as a world covered in diamond. That extreme planet clinging to its star and with an interior that could be saturated with carbon is 55 Cancri E. 55 Cancri A. 55 Cancri E is an uncomfortable planet. It doesn't fit neatly into our categories. It is not a hot Earth. It is not a mini Neptune. It is something in between, pressed up against its star until it almost brushes it, forced to live in a permanent state of tension. It lies about 41 light-years away in the constellation of Cancer. It is part of a system with several stars and several planets. The one that interests us is this rocky world, about 8 times more massive than Earth and nearly twice as large. At that scale, gravity at the surface would be brutal. Every step would weigh 2 or 3 times more. Every mountain would collapse under its own weight if it tried to reach the height of Everest. Its orbit is almost ridiculous. It completes a full lap around its star in less than 18 hours, a year that fits within a single Earth day. That is only possible because it is extremely close to its Sun, much closer than Mercury is to ours. That gravitational embrace has an immediate consequence. The planet is tidally locked. It always shows the same face to its star. One hemisphere lives in eternal daylight. The other never sees the dawn. For years, 55 Cancri E was famous for a very eye-catching label, the Diamond Planet. Some early models suggested that, because of its carbon-rich composition and the extreme pressures in its interior, a significant fraction of the mantle could be made of crystallized carbon. The image quickly went viral, a world covered in diamonds, a literal jewel floating in space. Reality, as usually happens, is less glamorous and more interesting. More recent observations have tempered that scenario. The amount of carbon appears to be lower than initially thought, and the physics of its interior is more complex than a simple ball of diamond. What we do know with considerable certainty is that this is a rocky world subjected to temperatures so high that its surface, on the day side, could be made of oceans of magma. Let us imagine that day side. The flow of radiation it receives from its star is hundreds of times greater than what Earth receives from the Sun. Estimates speak of more than 2000 degrees Celsius in the most illuminated region. At that temperature, rock melts. Part of the crust turns into a glowing sea where silicates behave like a viscous, shining liquid. The line separating surface and atmosphere becomes blurred. For a long time, there was another important doubt. Does it have an atmosphere or not? A world so scorched, so close to its star, should lose its gases quickly. Stellar wind and ultraviolet radiation tend to sweep away any volatile envelope. Some models suggested that 55 Cancri E could be almost a bare core, wrapped only in rock vapor. This is where a key piece of new astronomy comes into play, the James Webb Space Telescope. By analyzing how the star's light changes when the planet passes in front of and behind it, several teams have found solid evidence of an atmosphere. Not a friendly atmosphere like ours, but a dense mixture of carbon dioxide, carbon monoxide, and other heavy gases. A hot, thick, opaque envelope that traps even more heat that makes 55 Cancri E a milestone. It is one of the first rocky planets outside the solar system for which we have clear evidence of an atmosphere. On Earth, the atmosphere gives us pressure, protection, and thermal stability. On 55 Cancri E, the atmosphere probably does the opposite from our perspective. It raises the temperature, holds in heat like an extreme blanket, and fuels a brutal cycle between liquid rock, vapor, and condensation. The emerging picture is that of a planet with a day side covered in magma, from which silicates and other compounds evaporate. These vapors form an atmosphere loaded with heavy elements. Part of that gas flows toward the night side. There, as temperatures drop, some components could condense and fall back to the surface, perhaps as rain of molten rock that solidifies as it cools. It is not a water cycle, it is a cycle of stone. Moreover, the presence of a significant atmosphere opens another line of study: temperature gradients between day and night. If the planet had only a thin envelope of vapor, the thermal difference between hemispheres would be gigantic. With a thicker atmosphere, heat is distributed more efficiently. Observations of the planet's infrared brightness suggest that the night side is warmer than it would be if it were bare. That fits with the idea of efficient gas circulation carrying energy from the illuminated phase to the dark one. The pressure at the surface must also be extreme. With gravity much greater than Earth's and a thick atmosphere, the lower layers endure loads that would crush any known structure. There is no possibility of clouds like ours, made of suspended water droplets. If clouds exist, they will be made of silicates, metallic oxides, or exotic compounds floating above a sea of lava. Can life exist in such a place? As we understand it, no. The temperatures destroy any complex organic molecule. The radiation is intense. The surface is liquid, but not of water, of rock. 55 Cancri E does not fall into the category of habitable worlds, yet its importance does not depend on that label. Its value lies in showing us how far the idea of a rocky planet can be stretched and how matter behaves when subjected to extreme conditions. The atmosphere of 55 Cancri E also gives us a strategic clue. If we can detect, characterize, and measure gases on a world so hot and hostile, we will also be able to do so on somewhat cooler planets. The same methods we apply today to this hell of rock can, in the future, be applied to temperate worlds with liquid water. Every spectrum we obtain here is a dress rehearsal for the search for signs of habitability elsewhere. There is another quiet but key aspect: stability. A planet so close to its star should be subjected to intense gravitational tides. Its interior likely remains agitated with continuous volcanism that renews the surface and feeds the atmosphere with gases from the mantle. In a sense, 55 Cancri E is a planet that does not cool. It lives in a state of perpetual geological youth, forced by the proximity of its sun. If we stood there, we would not see a landscape of shining crystals, but a flat horizon of lava, a dense and reddish atmosphere, a constant glow. There would be no night, there would be no starry sky. Only the blazing disk of the star motionless overhead. HD 189733b HD 189733b deceives at first glance. In photos and illustrations, it appears as an intense blue sphere. One might think of oceans, white clouds, a more or less familiar climate. None of that is true. That blue does not come from water. It comes from a violent atmosphere loaded with glass particles and hot gases. This planet is about 63 light-years away, in the constellation Vulpecula. It is a gas giant, slightly smaller than Jupiter, orbiting a star similar to the Sun. The difference is in the distance. It completes one orbit in just 2.2 days. This means it is so close to its star that it almost brushes its innermost radiation layer. The energy it receives is hundreds of times greater than what Jupiter receives from the Sun. Like many of these close-in giants, HD 189733b is tidally locked. It always shows the same face to its star. One hemisphere lives in perpetual day, the other remains immersed in eternal night. Between them is a band of twilight where heat and cold meet. There, storms rage that never end. Temperatures on the day side reach around 1000 degrees Celsius, enough to break complex molecules, enough for many compounds to vaporize. The planet has no solid surface. It is a deep mixture of hydrogen, helium, and traces of other elements, compressed and stirred under high pressure. Its upper atmosphere is the main stage of everything we can observe. Why do we see it as blue? The explanation lies in the suspended particles. Everything indicates that its atmosphere contains tiny grains of silicate, that is, glass-like material. These particles scatter the star's light preferentially at short wavelengths, as happens in Earth's sky. But here there is no calm sky. There are high clouds of microscopic crystals floating in hot, turbulent gas. For years, HD 189733b was the best laboratory to study hot Jupiters. We have observed it with space telescopes and from the ground. We have seen it pass in front of its star and behind it. We have measured how the light changes when the atmosphere filters the stellar brightness. Every time the planet transits, its atmosphere leaves a signature in the spectrum. Absorption lines appear associated with water, sodium, potassium, and other compounds. One of the most striking results was the idea that on this world it could rain glass horizontally. The logic is simple. In the upper part of the atmosphere, silicate can condense into tiny crystals. Winds reach speeds of several thousand kilometers per hour, perhaps up to 7,000 or 8,000. At those speeds, any suspended particle is dragged from side to side. If those crystals fall, they do not do so in a straight line. They are propelled almost horizontally by supersonic winds. The image is not poetic, it is fluid physics. Hot air rises on the day side, relative cooling on the night side. Pressure differences generate massive currents. On a tidally locked planet, this machine never stops. The result is an eternally stirred atmosphere that redistributes heat around the globe. In recent years, we have refined this portrait even further. Infrared observations have allowed us to measure how the planet's brightness changes as it rotates in front of its star. This allows us to build a very rudimentary temperature map. We do not see continents or oceans, but we can know which areas are hotter and which are somewhat cooler. The maximum temperature is not exactly at the substellar point, the spot directly under the star. It is shifted eastward. This indicates that winds carry hot air before it can radiate all its energy into space. We have also detected more uncomfortable molecules, among them hydrogen sulfide, a gas that on Earth we associate with the smell of rotten eggs. On Jupiter and Saturn, this compound is part of the chemistry of their deep layers. Finding it on HD 189733b helps complete the puzzle of its composition. It tells us that we are not facing a chemically exotic world unrelated to our system, but an extreme variation of a type of planet we already know, the gas giant. There is another crucial aspect of this planet, atmospheric erosion. Being so close to its star, HD 189733b's atmosphere receives a constant bombardment of X-rays and ultraviolet radiation. It is likely slowly losing mass. Part of the outermost gas heats up, expands, and eventually escapes into space. Observations in certain hydrogen lines suggest that the planet may drag along a kind of faint tail, like a giant comet, invisible to the naked eye, but detectable in the spectrum. All of this makes HD 189733b a testing ground for our theories. It allows us to compare models of atmospheric circulation, cloud chemistry, heat transport, and mass loss. Each measurement constrains parameters. Each observed transit corrects a simulation. It is not just a strange world, it is a remote laboratory to understand how gas behaves at high temperatures under extreme irradiation. And yet, its blue color remains an important psychological detail. It reminds us how easy it is to project familiar images onto distant data. We see a blue planet and think of seas. We see an illuminated sphere and think of a surface under a sky. The reality is that this blue is the color of a hell of hot gas and crystals suspended in supersonic winds. Kepler 452b. Kepler 452b became famous very quickly, not because it is a confirmed habitable world, nor because we know what its surface looks like. It became a symbol for something more modest and at the same time profound. It is a planet that from a distance looks very much like what we would expect from a larger Earth, orbiting a star very similar to the Sun in a strangely familiar orbit. It is about 1,800 light-years away, in the constellation Cygnus. It was discovered by the Kepler mission by analyzing small dips in the brightness of its star. Every time the planet passed in front, it stole a tiny fraction of the light. That periodic repetition, always with the same depth and the same interval, revealed its presence. The host star is type G, very similar to the Sun, but slightly older and slightly more luminous. The data tell us that Kepler 452b has a radius about 1.6 times that of Earth. We do not know its exact mass, but typical relationships between size and composition indicate that, with high probability, it is a rocky or rock-dominated world, perhaps with a denser envelope of water or volatiles. It is not a miniature gas giant. It falls into the category we call super-Earths. Its orbit is perhaps the most striking fact. It takes about 385 days to complete a full revolution. That is, its year is just a little longer than ours. The distance to its star falls right in what we call the habitable zone. This is the range of distances where, if other conditions are right, liquid water could exist on the surface. This guarantees nothing. Venus and Mars were once in that range, and today they are very different places. But statistically, it is in this band that we first look for potentially temperate worlds. To imagine what Kepler 452b might be like, we have to combine several effects. Being slightly larger, its surface would have higher gravity. A human would feel their weight increase by 50 or 60% depending on the actual mass. This affects the atmosphere. Greater gravity helps retain gases for longer. It is possible that the planet has a thicker atmosphere than Earth, provided it has not been stripped away by extreme processes. The star, in turn, complicates the picture. Estimates suggest it is about 1.5 billion years older than the Sun. Over time, Sun-like stars increase their brightness. A star somewhat older than ours emits more energy. This means that even if Kepler 452b orbits in a geometric habitable zone, it could be receiving more radiation than Earth did when life became established here. That detail opens a range of possibilities. One scenario is that the planet went through a process similar to Earth's with oceans and carbon cycles, but is now entering a Venus-like phase. More light means more evaporation. More water vapor in the atmosphere strengthens the greenhouse effect. The temperature rises, even more water evaporates. At some point, the ocean could turn into a dense, hot vapor atmosphere. Over time, ultraviolet radiation breaks apart water molecules and hydrogen escapes into space. The end result, after hundreds of millions of years, could be a dry world with a thick carbon dioxide atmosphere and an overheated surface. Another, more optimistic scenario is that mechanisms like plate tectonics and a very active carbon cycle stabilize the climate. In that case, Kepler 452b could have maintained the liquid water for billions of years, longer than Earth. If life arose there, it would have had a longer evolutionary window. In such a context, we could be looking not just at a cousin of Earth, but at a more mature version of what a habitable planet can become. The problem is that, for now, we cannot distinguish between these options. We do not have spectra revealing its atmosphere. We have not yet measured its mass precisely. What we do have is a concrete example of what we are looking for when we think about other Earths. A Sun-like star, a one-year orbit, a moderately larger radius, a reasonable position in the habitable zone. Kepler 452b forces us to think in terms of timescales. Earth is about 4.5 billion years old. Microscopic life appeared very early, but complex life took much longer. Only in the past few 100 million years have forests, insects, and land vertebrates existed. Only in the past few 100,000 years has our species existed. In cosmic terms, it is a blink of an eye. If Kepler 452b has enjoyed temperate conditions for a longer period, the question is not just whether it can be habitable. The question is how long it has been. How many geological, climatic, and biological cycles could have developed there? We do not have data to answer, but the very possibility changes the way we think about the problem. We are not looking only for planets like Earth now. We are also looking for planets that are like Earth was or could be in a billion years. At this point, another hard physical limitation appears. Distance. 1,800 light years is an abyss. Even if tomorrow we confirm that Kepler 452b has oceans, continents, and an oxygen-rich atmosphere, it would not be a destination. It would be data. With current technology, even the fastest probes could not reach that world in times that make sense for us. The limit is not imagination, it is the speed of light. This impossibility of direct visitation has an interesting consequence. It forces us to be more rigorous about what we infer from small signals. A drop in brightness of less than 1%, a slight variation in transit time, a weak and noisy spectrum. With that, we build images of entire worlds. We know it is fragile, but we also know it is the only available path. Kepler 452b thus acts as a distant mirror. It reflects questions about our own planet. How long will Earth remain in stable conditions for complex life? What will happen when the sun becomes brighter? To what extent can geology and biology buffer that change? What we imagine for that other world is, in part, a mental rehearsal of our distant future. In the context of this journey through extreme planets, Kepler 452b is almost a break. We have come from hells of gas, glass, and magma. Here, at least in principle, we can draw oceans, water clouds, continents of solid rock. But that apparent familiarity should not deceive us. This planet opens a different kind of rarity, not of temperature or exotic chemistry, the rarity of time, worlds that have seen more sunrises than ours, worlds that may have already crossed the threshold that Earth will one day cross. Rox 42bb. Rox 42bb lives in a region of space where almost everything is unstable. It is a planet that orbits a young stellar system surrounded by disks of gas and dust. Nothing there is finished. Everything is under construction, and yet In the middle of this chaotic scene, there is already a giant world that we can see directly as a point of light. It is about 440 light years away, in the constellation Ophiuchus. It does not orbit a single star, but a binary system. Two young suns that have not yet fully settled. Around them, this planet traces a very wide orbit. Tens or even hundreds of times the distance between the Earth and the Sun. Completing one orbit can take centuries. ROXNE 42BB was not discovered by transit. Like many other exoplanets, we did not see it block part of its star's light. We saw it literally in a photo. Telescopes with adaptive optics corrected in real time were able to separate its faint infrared glow from the much brighter light of the stellar system. In those images, it appears as a tiny dot, but that dot is a gigantic world. Estimates indicate that it has around 9 Jupiter masses, maybe a little more, maybe a little less. On that scale, it is already approaching the limit we use to differentiate a giant planet from a brown dwarf. It is not a strict physical boundary, it is a convention. Above about 13 Jupiter masses, an object can briefly ignite deuterium fusion in its interior. Below that, it cannot. ROXS 42BB seems to stay on the planetary side of that line, though very close. Its youth is key. It is only a few million years old. In cosmic terms, it is a newborn. It still retains much of the heat from its formation. That internal heat makes it glow in infrared, not because it is receiving a large amount of radiation from its stars, but because its own interior is emitting energy into space. It is still a glowing planet in terms of heat. This gives us an advantage. In this case, we do not rely on the trick of seeing its shadow against the star. We can study the light it emits itself. By analyzing its spectrum, astronomers have found hints of water in the atmosphere, carbon monoxide, and other molecules that allow us to estimate temperatures and pressures. Its atmosphere is believed to exceed 1,000 degrees Celsius, a young gas giant wrapped in dense clouds of particles and molecules, still in changing equilibrium. The existence of such an object so far from its stars poses an interesting problem. Classical planet formation theories are based on disks of gas and dust that become thinner as we move away from the central star. Closer in, there is more material, more collisions, more cores that can grow and attract gas. Farther out, material is scarce, forming a giant planet tens of astronomical units away by the classic mechanism of rock and gas accumulation would be very slow. One possibility is that ROXS 42BB did not form like a typical planet, but as a kind of failed mini-star. A fragment of the disk itself collapsed due to gravitational instability, separated, and became an independent object, bound to the system by gravity, but with a different history from a normal Jupiter. In that scenario, what we call planets and brown dwarfs blend into a continuum. There are not two separate families, but a range of objects formed by processes that in some cases overlap. Another possibility is that the planet formed closer in and was ejected to a distant orbit after a gravitational encounter with another giant. Exchanges of energy and angular momentum can fling one planet outward and perhaps eject another into interstellar space. Numerical simulations show that this kind of chaotic dance is possible in young systems. ROXS 42BB could be the survivor of an old battle between colossi. In either scenario, the conclusion is similar. Young planetary systems are violent. The image of planets growing in place in an orderly fashion is too simple. There are collisions, ejections, rapid migrations. Some worlds fall into their stars, others are thrown into deep space. Others remain in wide, eccentric orbits, like exiles still tied to their original home by a very long gravitational rope. From an observational point of view, ROXS 42b is a treasure. Exoplanets that we can see directly are few. Most of the thousands we know are detected by indirect methods. Having a young, massive and luminous giant that stands out in infrared against the sky background allows testing and refining direct imaging techniques. It allows experimenting with coronagraphs, adaptive optics, stellar light subtraction algorithms. Every improvement in this field brings us closer to the dream of one day seeing even fainter points, smaller planets, even rocky worlds. Furthermore, studying its atmosphere helps us understand how these giants change over time. A Jupiter like ours has already cooled considerably. It emits some internal heat, but at a relatively low rate. A young ROXS 42b, on the other hand, is a furnace. Its atmosphere is dominated by processes that on Jupiter we can only infer from models. Dust clouds, chemistry out of equilibrium, strong temperature differences between layers. Imagine for a moment that we could get close. We would not see a solid surface. We would see a sphere of gas crossed by bands, vortices and storms. Its glow would be more intense in infrared than in visible light. Around it, the two stars of the system would illuminate the sky variably. In the distance, fragments of the protoplanetary disk, rocks, ices, remnants of other planetary cores in formation. The role of ROXS 42b in this journey is to show the upper extreme of the planetary scale in young systems. How far a planet can grow before it starts to resemble a failed star, and how that limit is not only a matter of mass but also of origin. What processes formed it? Where? In what environment? Kelt 9b. Kelt 9b is the closest thing we've found to a star in the form of a planet. It does not shine by nuclear fusion, but its atmosphere lives at temperatures that, until recently, we only associated with the outer layers of some small stars. It is a gas giant that has taken the idea of a hot planet to the extreme. Its star, Kelt 9, is about 670 light-years away in the constellation Cygnus. It is much hotter than the Sun. Its surface exceeds 10,000 degrees. It is a star on the border between types A and B, massive, luminous, bathing its surroundings in extreme ultraviolet radiation. Around it, Kelt 9b orbits so close that it completes a full orbit in about 36 hours. The distance to the star is barely 1/100th of the separation between the Earth and the Sun. With that proximity, tidal locking is inevitable. The planet always shows the same face to its star. One hemisphere lives in a perpetual day that never ends. The other remains trapped in a night that never sees sunrise. There are no daily cycles, only a constant bombardment of photons on one side and a dimmer, yet equally hot darkness on the other. On the day side, temperatures approach 4,600 Kelvin, over 4,300 degrees Celsius. That is comparable to the surface of a Type K star. At that temperature, molecules do not survive. Molecular hydrogen breaks into atoms. Water, carbon monoxide, any complex compound dissociates. The atmosphere becomes a gas of atoms and ions, like the outer atmosphere of a star. On more moderate exoplanets, elements such as iron or titanium are usually trapped in oxides or dust grains. On KELT9b they are not. Here, atoms of iron and titanium have been directly detected in gaseous form, even ionized. The heat is so intense that metals vaporize and mix with the hydrogen and helium of the atmosphere. High-resolution observations have also revealed ionized calcium and very broad hydrogen lines, acting as natural thermometers for this extreme envelope. The result is an atmosphere that no longer resembles that of a typical planet. It looks more like the diffuse edge of a star. This atmosphere is also at the edge of its stability. The outer edge of KELT9b approaches what we call the Roche lobe, the region from which the star's gravity begins to efficiently strip gas. Observations in the hydrogen H-alpha line show a swollen, extended envelope that nearly doubles the planet's radius. It is an atmosphere that is escaping, dripping hydrogen into space and partly toward the star itself. Estimates of the loss rate are brutal on a human scale. Tons of gas per second. Translated to long timescales, it amounts to tens of Earth masses per billion years. It will not disappear tomorrow, but over the star's lifetime it could lose a significant fraction of its gaseous envelope. In the distant future, KELT9b could be reduced to a more compact core, perhaps rocky or metal-rich, still orbiting extremely close to its sun. There is another key process occurring on this world. Molecular hydrogen does not only break apart on the day side. This dissociation and its reverse, recombination, participate in heat transport. On the illuminated side, photons break H2 into two atoms. That break absorbs energy. On the night side, when the atoms recombine into molecules, they release part of that energy. It's as if the gas itself is chemically carrying heat from one side to the other. This cycle helps reduce the temperature difference between day and night. Observations of the planet's brightness as it rotates in front of its star show something curious. The night side remains extremely hot. There is not as huge a contrast as in other hot Jupiters. This indicates very efficient energy redistribution. Heat flow does not stop at the terminator. The continuously stirred atmosphere carries atoms, ions, and energy in an almost global circulation. At the same time, thermal spectra reveal a temperature inversion in the upper layers. Instead of cooling with altitude, the atmosphere in certain regions increases in temperature as it rises. This suggests that absorption of ultraviolet radiation by atomic metals and lines such as ionized calcium heats the upper layers, a structure more like the stratosphere of a star than that of a classical planet. If we could look up close, we would not see clouds as we understand them. At these temperatures, any condensates are destroyed. The atmosphere is a clear fluid, dominated by absorption and emission lines of individual atoms. The star's light passes through this envelope and emerges marked by iron, titanium, calcium, excited hydrogen. That signature is what we collect with our spectrographs and translate into models. The contrast with a gas giant like Jupiter is total. Jupiter has ammonia cloud bands, water storms, a cold stratosphere. KELT9b has an almost purely atomic atmosphere at temperatures that would melt any terrestrial metal. Yet both are products of the same general process. Gas trapped by a star in a protoplanetary disk. One formed far away, cooled and stabilized. The other became trapped in an impossible orbit, stuck to an enormous star. KELT9b. 9b also forces us to think about the limits of classification. If a planet can reach stellar temperatures and an almost fully ionized atmosphere, does it still make sense to call it a planet in the same sense we use for Earth or Neptune? The main difference is not physics, but origin. It does not generate its own heat through internal fusion. It is a passive object, heated from the outside. But this conceptual nuance becomes blurred when its appearance resembles a star so closely. Despite being so close to a luminous star, Celt 9b does not appear particularly reflective. Its geometric albedo is low. It absorbs most of the light it receives. Most of the brightness we detect comes from its own thermal emission, not reflected light. In practice, it is a scorched world that behaves more like an ember than a mirror. Not all extremes are expressed in heat. Some are expressed in near total darkness. There are planets that, instead of shining like furnaces, seem to swallow light. Worlds that reflect a tiny fraction of the radiation they receive, darker than coal, almost invisible against the backdrop of space. 3ES 2b. 3ES 2b is a planet that almost doesn't exist at first sight. Not because it's small, it's as large as Jupiter. Not because it's far from its star, it's very close. What makes it unusual is something else. It barely reflects light. It is, as far as we know, the darkest discovered planet. It orbits the star GSC 03549-02811, about 750 light-years away, in the constellation Draco. Its orbit is short. It completes a revolution in about 2.5 days. It is only 0.035 astronomical units from its star, much closer than Mercury is to the Sun. This makes it what we call a hot Jupiter, a gas giant stuck close to its Sun, receiving hundreds of times more radiation than Jupiter. Its mass is slightly greater than Jupiter's. Its radius is too. There is no doubt that it is a gas giant. What is puzzling is how it interacts with light. The key parameter here is albedo. It is essentially the fraction of light an object reflects. Earth reflects about 30% of sunlight, Jupiter about 50%, coal around 4 to 5%. TRES-2b reflects less than 1%. The most refined models suggest a geometric albedo of just 0.04%. That makes it darker than the blackest coal, darker than black acrylic paint. From a distance, it practically blends with the background of space. The Kepler telescope barely detected a tiny variation in the system's brightness, on the order of a few parts per million, associated with the planet's transit and the changed phase of its day and night. How can a giant planet be so black? Part of the answer lies in what it doesn't have. Jupiter and Saturn appear relatively bright because the cold atmospheres allow the formation of high clouds of ammonia and other ices. Those clouds act like mirrors. They reflect light well. TRES-2b is too hot for that. At temperatures around 1800 Kelvin, those clouds cannot exist. Instead of bright surfaces, its atmosphere is dominated by gases that absorb a visible light. Sodium and potassium, for example, have very broad lines in the visible spectrum. If present in large amounts, they consume photons of many wavelengths. Other absorbers may also be present, like complex molecules or photochemical haze particles. The result is a world that swallows almost everything it receives. Kepler not only detected the transit, it also measured the phase curve. That is, how the total light of the system changes as the planet shows different phases toward us during its orbit. On a bright planet, That curve has a clear amplitude. We see more light when the day side is facing us and less when we mainly see the night side. On TRES2b, that variation is tiny. The planet contributes to a change of just a few parts per million in the total flux. This requires models in which the visible brightness is mainly due to thermal emission, not reflected light. Despite being so dark, TRES2b is not completely black. Its temperature causes it to emit thermal radiation like a faint ember. That glow is stronger in the infrared, but a small fraction falls within the visible range. If we could get close enough, we would see a sphere that looks like glowing coal, very faint, reddish, silhouetted against its star's glare. Most models agree that the planet is tidally locked. Like other hot Jupiters, it always shows the same face to its star. The day side is permanently exposed to a photon bombardment. The night side remains warm thanks to winds that redistribute part of that energy. Kepler data and infrared observations suggest that the temperature difference between the two sides is significant, but not extreme. This indicates some degree of heat circulation, though not as efficient as on other hot giants. TRES2b is also a good test for our theories about exoplanet atmospheres. Models explaining its darkness use an additional opacity layer in the visible part of the spectrum. Something in the atmosphere absorbs more light than expected from sodium and potassium alone. The exact nature of this absorber remains unknown. It could be fine particles, products of photochemical reactions in the upper atmosphere. It could be exotic molecules stable only at very high temperatures. The interesting part is that the planet forces us to include these ingredients for the models to match the observations. The contrast with other hot Jupiters is instructive. Kepler 7b, for example, has a much higher albedo. Its clouds seem to reflect much of the light it receives. This shows that not all close giants are the same. Some are mirrors, others, like TRES2b, are light wells. This diversity suggests differences in composition, cloud formation, irradiation history, and possibly the metallicity of host stars. From a technical perspective, detecting such a dark planet was a precision achievement. Measuring variations of a few parts per million in a star's brightness requires extreme telescope stability and careful statistical analysis. The detection of TRES2b's visible light, announced in 2011, became a milestone. It showed that we could begin to study the reflectivity of individual exoplanets, not just their sizes and orbits. It also reminds us something about the concept of darkness in the universe. Nothing is completely dark. Even this planet, darker than coal, emits faint light because of its temperature. Even the space between galaxies vibrates with photons from the cosmic background and distant stars. Absolute darkness is an idealization. TRES2b is, for now, our best example of how close a real world can get to that idea. GJ504b. GJ504b is a young planet. It shows in everything. In its brightness, its temperature, and its strange pink color, which does not fit the usual palette of gas giants we know. It is about 57 light-years from Earth in the constellation Virgo, orbiting a star similar to the Sun, known as Gliese 504 or 59 Virginis. Its star is slightly hotter and brighter than the Sun, but it is not a blue monster like KELT 9b. It is a kind of close cousin of our star. This makes the system particularly interesting, a strange giant orbiting a star very similar to ours. The first peculiarity of GJ504b lies in how it was discovered. It was not through transit, not through radial velocity, it was through direct imaging. In 2013, using the Subaru telescope in Hawaii, astronomers managed to separate the faint light of the planet from the glare of its star. There, in the infrared, a clear point appeared far from the central star, a world of about 4 Jupiter masses, visible due to its own internal heat. That point of light was neither white nor yellowish. The data indicated a magenta hue, a dark pink. Some NASA releases described it as similar to a dark cherry blossom, a dirty pink glowing from within. This hue is the signature of a planet that is still cooling. The energy it emits does not come only from the light of its star. It comes from the heat of its formation, still escaping from its interior. The second peculiarity is the distance from its star. GJ504b is about 43.5 astronomical units from its Sun, slightly farther than Neptune is from ours. Its orbit lasts about 260 years. It is a very massive giant, but parked very far away. At that distance, in classical planetary formation models, it is hard to gather enough solid material to build a core that then attracts so much gas. It is like trying to assemble a giant planet at the edge of the workshop, where almost no parts remain. Its mass, according to the best estimates, is about 4 times that of Jupiter. Its size is only slightly larger than Jupiter's, around 1.1 Jupiter radii. This means it is dense for a young gas giant. It is not a puffed-up bubble from nearby radiation like hot Jupiter's. It is a heavy and compact planet, storing much of its mass in a volume relatively similar to Jupiter's. The age of the system is another key fact. Gliese 504 and its planet are about 160 million years old. Compared to Earth's 4.5 billion years, it is almost a cosmic teenager. It has not yet had time to cool completely. For this reason, even at a great distance from its star, its atmosphere glows faintly in the infrared. It is a giant still shining from the thermal memory of its birth. The atmosphere's temperature is around 460 degrees Fahrenheit, about 240 degrees Celsius. It is not a hell like Kelt 9b, but it is also not a cold world. It is the kind of temperature we would expect in a moderate oven, not on the surface of a distant planet. This combination of large distance, youth, and intermediate temperature gives rise to a peculiar atmosphere. Models suggest that GJ504b has an atmosphere rich in hydrogen and helium, with traces of water, methane, and probably complex clouds. At these temperatures, methane should start appearing significantly, but infrared observations show less methane than expected. This indicates that the atmosphere is out of chemical equilibrium, stirred by currents mixing layers at different temperatures. Its pink color also requires explanation. The hue comes from how its atmosphere emits and filters light. The dominant thermal emission is in the near-infrared, but part shifts toward shorter wavelengths. The presence of clouds and molecules like water reshapes the spectrum, dampening some bands and leaving others freer. The result, when translated to an approximate visible color, is that faint magenta. It is not pink, like a painted wall, but a glow that our eyes would interpret as warm violet if we could see it up close. In terms of dynamics, GJ504b is also a challenge. If it formed where it is, so far out, the accumulation of a massive rocky core would have been very slow because the density of solids in the protoplanetary disk is low in those regions. One possibility is that the disk surrounding Gliese 504 was particularly massive and cold, favoring gravitational instability. In this scenario, entire fragments of the disk collapse and form gas giants at once, without first needing to build a rocky core. Another possibility is that the planet formed closer to the star and migrated outward, pushed by interactions with the disk or other massive planets. Outward migration is not as intuitive as inward migration, which gives rise to hot Jupiters, but numerical simulations show that in systems with multiple giants, gravitational encounters can exchange energy, ending with one planet in a wide orbit and another completely ejected from the system. GJ504b could be the survivor of that early dance. From an observational standpoint, GJ504b is valuable for another reason. It is one of the lightest planets we have directly photographed around a Sun-like star. This makes it an ideal target for testing direct imaging techniques for relatively cold, low-mass exoplanets. Every new observation of this world helps refine coronagraphs, stellar light subtraction algorithms, and methods for extracting spectra from extremely faint light points near bright stars. Imagine what this means for the future. If we can already isolate the glow of a giant 4 times more massive than Jupiter at tens of astronomical units around a Sun-like star, we are taking the first steps towards something much more ambitious, seeing super-Earths and, one day, Earth-sized planets through direct imaging. GJ504b is a step on that technical ladder. Moreover, its youth gives us an early snapshot of what a newly formed giant may look like on the outskirts of a system. Jupiter and Saturn had to go through similar stages, though today they no longer glow with a magenta hue. Seeing a planet at this phase allows us to test models of cooling, gravitational contraction, and atmospheric evolution. Comparing young worlds like this one with older giants, we can, in a way, reconstruct the thermal biography of giant planets. HR5183b. HR5183b is a planet that doesn't know how to stay still. It doesn't trace a calm orbit like Earth. It doesn't rotate in an almost perfect circle like Jupiter. Its path around its star is a gravitational whip, a long, slow and eccentric journey that takes it from regions similar to Jupiter's orbit to areas beyond Neptune on each pass. It is about 103 light-years away, orbiting a star called HR5183 in the constellation Virgo. The star is similar to the Sun in mass and slightly more luminous. The planet, however, behaves like a giant comet. Measurements indicate a very eccentric orbit, with an eccentricity close to 0.84. This means it spends part of the time relatively close to its star and the rest in icy remoteness, describing a very elongated ellipse. The biggest peculiarity of HR5183b is not just its orbit. It is that we discovered it without seeing it complete a full orbit. Normally, to determine a planet's orbit, using the radial velocity method, we need to observe multiple cycles. We see how the star moves slightly toward and away from us due to the planet's pull. These repeated velocity changes reveal the orbit. In this case, astronomers had been observing HR5183 for almost 20 years. The data showed a strange pattern, a long stretch with moderate changes, followed by a large jerk in the star's velocity. It was like seeing only a fragment of the full dance. Still, the magnitude of the shift and the shape of the curve were enough to reconstruct the planet's orbit. Its period was estimated between 45 and over 100 years, with a trajectory taking it from about 3 astronomical units to over 30. HR 5183b's minimum mass is around 3 Jupiter masses. Minimum, because the radial velocity method only gives a projected value depending on the angle of the orbit as seen from Earth. Even considering this lower limit, we are talking about a serious giant, a world capable of reorganizing an entire planetary system on its own. How does an orbit like this form? The most likely explanation is a violent gravitational interaction in the past. Imagine a system with at least 2 gas giants. For millions of years, their orbits slightly cross. Each close encounter exchanges energy and angular momentum. In one of these encounters, the result can be drastic. A planet is ejected from the system or sent onto a very wide orbit. The other is trapped in a very eccentric trajectory. HR 5183b seems to be the survivor of one of those battles. It is not as close to the star as a hot Jupiter. It was not ejected into interstellar space. It remained in an unstable middle ground. A giant that spends part of its time far and part close, like a pendulum, stretching and compressing with each swing. If there were inner rocky planets in the system, their lives would not be easy. Every time HR 5183b approaches periastron, the point of closest approach to the star, its gravitational field could perturb the orbits of other bodies. Small accumulated changes can destabilize inner worlds, tilt them, lengthen their orbits, or even eject them. In some numerical models, an eccentric giant like this could almost entirely clear the habitable zone over time, either throwing planets inward where they crash into the star or outward into deep space. However, there are scenarios in which such a planet coexists with terrestrial worlds. If the orbits are well separated and in certain resonance configurations, stability can be maintained for billions of years. From a distance, without direct data on other planets in the system, we can only speculate. What we do know is that HR 5183b is a powerful dynamic agent. Its mere presence shapes the rest of the system. Extreme eccentricity also has consequences for the planet itself. At its closest point to the star, it receives much more radiation than at its farthest point. The amount of solar energy it receives can vary enormously between periastron and apastron. This means its atmosphere undergoes cycles of heating and cooling over the planet's year. We do not yet have a detailed map of its atmosphere. The method by which we detected it does not allow for observing transits or obtaining direct spectra, but we can imagine some general effects. Close to the star, the atmosphere heats up, expands, may intensify winds, and cause chemical changes. Far from it, it cools, contracts, and allows different combinations of molecules and clouds. The changes would not be as rapid as seasonal weather on Earth. Here we are talking about adjustments on a decade scale. A planet with very long seasons determined by its distance from its sun. To visualize its orbit, it's worth comparing it to something familiar. If we place the star HR 5183 where the Sun is, the planet's periastron would be in a zone comparable to Jupiter's orbit or slightly inward. Its apastron would extend beyond Neptune's orbit. In a single orbit, HR 5183b travels through almost the entire system, crossing regions that, in our case, are occupied by asteroid belts, gas giants and icy worlds. From a broader perspective, this planet is an observational proof of something formation models had already suggested. Planetary systems can be far more chaotic than ours. The nearly circular arrangement of orbits in the solar system is a relative stroke of luck. It is not a universal rule. There are systems where gas giants fight, eject each other, and leave survivors on distorted orbits. This kind of orbit also complicates the detection of possible companions. A planet on such an elongated path can mask or contaminate signals from other, less massive bodies. Measurements must continue for decades to properly separate each contribution. HR 5183 is an example of slow science. Observations taken over 20 years, combined from different observatories, allow reconstructing the history of a single planet. There is no shortcut. There is accumulated patience. In our journey, HR 5183b represents the extreme of orbital dynamics. So far we have explored temperature, color, darkness, composition. Here the main character is motion, a world that swings toward its star and then moves away, in a cycle lasting longer than many human lifetimes. A planet that by its very existence reminds us that the architecture of planetary systems can be radically different from our own. PSRB 1620-26b Methuselah. PSRB 1620-26b is, above all, a date, not a coordinate in space, but in time. When we think of planets, we usually imagine them as settings, places where oceans, mountains and atmospheres could exist. This one, however, first forces us to look at the cosmic clock. It is a world that already existed when the universe was young, and the Milky Way was just beginning to organize itself. It is about 12,400 light-years away, in the constellation of Scorpio, within the globular cluster M4. A globular cluster is a compact sphere of hundreds of thousands of very old stars, bound by gravity almost since the galaxy's beginning. The estimated age of M4 is around 12.7 billion years. Our Sun, by comparison, is 4.6 billion years old, Earth even less. PSRB 1620-26b formed when neither the Sun nor the Earth existed yet. Its nickname, Methuselah, is not accidental. Estimates indicate an age of about 12.5 to 13 billion years. Almost the entire known history of the universe is condensed into a single world. It is a gas giant, with a mass about 2 or 3 times that of Jupiter, orbiting roughly 23 astronomical units from the center of mass, a distance comparable to Uranus's orbit around the Sun. Each complete orbit takes roughly 100 years. The star it orbits is not a normal star either. In fact, there are 2. PSRB 1620-26b moves around a binary system composed of a pulsar, a neutron star spinning hundreds of times per second, and a hot white dwarf. The pulsar, the collapsed remnant of a supernova, emits extremely regular radio pulses. The white dwarf is the bare core of a star similar to the Sun that exhausted its fuel and expelled its outer layers. Both objects orbit each other at a distance of about 1 astronomical unit, completing a turn every 6 months. How do you detect a planet in a place like this? There are no transits we can see with telescopes like Kepler. There is a clock. The pulsar emits radio pulses so regularly that any small gravitational tug leaves traces in the timing of the pulses we receive. In the early 1990s, astronomers studying PSRB 1620-26 noticed that the signals did not fit a simple binary orbit. There were additional oscillations, tiny variations in the pulse period, indicating the presence of a third body. By analyzing these changes, they concluded that the extra object could not be a star. Its mass was too small. It had to be a planet. The story of how this planet got there is almost as interesting as its age. In a globular cluster, stars are so close together that gravitational encounters are much more frequent than in the quiet neighborhood of the Sun. It is very likely that the planet did not form around the pulsar, but around a star that is now the white dwarf. At an early point, that star and its planet formed a common system, perhaps with other companions. Later, that system crossed paths with the pulsar in the dense cluster environment. The result was a gravitational exchange. The star with its planet became trapped in orbit around the pulsar, and the pulsar's former companion was ejected. Then came another dramatic phase. The companion star began to age, inflated like a red giant, and started transferring matter to the pulsar. This flow of gas acted like a torrent of energy and angular momentum. It re-accelerated the pulsar into a millisecond pulsar with extremely rapid rotation and very regular pulses. For a time, the system was an intense source of X-rays fueled by material falling onto the neutron star. When the red giant exhausted its outer layers, what remained was the white dwarf we see today, still hot. The planet survived this entire process at a sufficient distance to avoid being destroyed or swallowed. Now the result is a peculiar triple system: a millisecond pulsar, a white dwarf, and a gas giant, all gravitationally bound. The planet orbits both in a circumbinary orbit. From the hypothetical surface of a moon on this planet, the sky would be full of densely packed stars. M4 is a hive, hundreds of thousands of suns concentrated in a relatively compact region, very different from the dark, empty sky we see from Earth. On the horizon, the pulsar and the white dwarf would appear as intense, small, but highly energetic points. The very existence of Methuselah forces us to rethink the timeline of planetary formation. For years, it was thought that globular clusters, poor in heavy elements like iron, carbon, or oxygen, were not good places to form planets. These elements are the building blocks of rock and solid cores. Without them, it is hard to imagine protoplanetary disks capable of generating worlds. Yet here we have a planet in a very old globular cluster. This suggests that planet formation can begin earlier than previously thought, even in metal-poor environments. Or the capture processes in dense clusters can assemble unexpected systems. It also raises an inevitable question. Could life have existed at some point on such a world, or on its hypothetical moons? There is no evidence, and the current environment is not friendly. The pulsar's radiation is intense. Environmental changes must have been violent. But in terms of timescale, Methuselah has had billions of years to experience different conditions, perhaps before the supernova phase, perhaps before its original star collapsed. The planet could have gone through very different stages than the configuration we see today. From a technical point of view, this world is a triumph of method. We have not seen it. We do not have an image. All we know comes from how it alters the regularity of a natural clock, the pulsar. It is another reminder of an idea that recurs throughout the documentary. Most of what we know about these planets comes from small anomalies in light or time, curves that deviate slightly, pulses that arrive a little early or a little late. From these irregularities, we build reasonable stories about the size, orbit, age, and environment of worlds thousands of light years away. On our journey, we have passed through iron and glass hells, magma oceans, giants so hot they seem like stars, and so dark they almost disappear. We have seen newborn planets, pink and bright, and giants traveling in whip-like orbits. We end with Methuselah, a planet that is more a witness than a setting. It has survived the birth and death of stars. It has crossed a dense cluster for billions of years. It has witnessed much of the history of the cosmos. This is perhaps the deepest message this world leaves us. The diversity of planets is not just a list of oddities. It is a way to measure how far matter can withstand extreme conditions. What structures a gas disk can take under different histories of radiation, gravity, and time, and, by extension, how special or common a planet like ours can be. When we look at Methuselah, we do not see a promise of travel. We will never go there. What we see is silent proof that planets have been forming almost from the beginning in environments very different from our own. If a gas giant could be born and survive in the core of a globular cluster orbiting a pair of stellar corpses, then the universe has had billions of opportunities to repeat and surpass what happened here. Amid iron rains, lava seas, glass winds, pink giants, and elders who have seen almost the entire history of the cosmos, our own Earth is just another point in that statistic. A temperate, medium-sized world orbiting a medium star in any arm of a spiral galaxy. None of this diminishes its importance. On the contrary, knowing how rare the universe can be, and yet finding ourselves in a place where the sky is habitable to our gaze, makes this small planet seem, if anything, even more extraordinary.